So is it audible? Hello. Hello. Anyone, can you please reply? Is it audible?
Yes, sir.
Okay. So in the yesterday class, we were discuss about the current transformer, and in the today class, we are going to discuss about the potential transformer. We are going to discuss here now. So the current transformer, it is going to reduce the current from higher current to the lower current. The potential transformer also, it is going to step down here, the step down from the higher voltage to the lower voltage. This one also, it is going to reduce the voltages from higher to the lower resistances. Okay, I will lock the meeting, better option, because students already 10. One more minute, I will wait. At 10:10, I will lock the meeting. So see here, three-phase supply we have considered here now. Three-phase supply AC system. For each phase, the potentiometer we are going to use. For the one phase, I have connected here. We have tapped here now. The parallel path we have tapped here now, and we have connected one fuse for this one. And the primary winding I have used here. The primary winding I have used. The other end of primary winding is earthed over there here now. To get the closed conducting path, this is earthed here now. It is earthed here now. And the fuse we have provided, whenever it is required, we can remove that one also. Whenever it is not required, on that condition, we can remove that. So I will lock the meeting. Where is the option of locking the meeting? I disable the remote controls. Security. Meeting is locked. I have locked the meeting. No one else can join here. Okay. So RYB three-phase supply is there here now. For one phase, I have tapped the primary winding I have tapped and connected to this one here now. And other end of the primary winding, it is grounded or earthed here. Okay. So the secondary winding is connected to the voltmeter. The potential meter, it is going to measure two voltages only here. So it is used a voltmeter, and this voltmeter has very large resistance is there here now, and it is also the other terminal, it is connected to the ground or earth here now. Voltage across this potentiometer one end across to the earth only, we are going to measure the voltage drop here. Total voltage it is going to measure here now. With respect of earth, we are going to measure here now. So this one we are going to use, we can use this one for the measurement of power, for the measurement of energy, for the measurement of voltmeter, whatever we can connect here now in this place of voltmeter here now. So the definition of potential transformer, it is a first instrument transformer. It is an instrument transformer and used for the transformation of voltage from higher value to the lower value. It is going to transfer the higher value of voltage to the lower value of voltage here. It is going to transfer the higher value of voltage to the lower value of transfer voltage here. Now it is a device, the instrument transformer device here. This is one. And you can observe here now. What is this one? This is a primary winding. We can say that one. I'll take the annotate. Just try to give the interaction. This one is primary winding. This one is secondary winding. We are going to tell that one. The primary winding is connected to the line here now. The AC line, power line, it is connected in parallel here now. And secondary winding is connected to the voltmeter here now. Comparing these two, which winding number of turns are more here now? Which winding number of turns are more? Can anyone tell?
Primary.
Primary winding, the number of turns are more. According to the principle of the transformation ratio, number of turns are more. Which side the number of turns are more? That side voltage will be high. So the number of turns are more here. So the voltage primary is high here, and the secondary has only few number of turns are there, only 3 to 4 turns are there. So the higher voltage is stepped down or transformed into the lower voltage here. Is transformed into lower voltage here now. So potential transformer is the instrument transformer which transforms the high voltage value to the low voltage value here. Now that is the definition of this potential transformer. See here, the potential transformer may be defined as an instrument transformer. It is an instrument transformer. It is used for the transformation of voltage from higher value to the lower value here now. And this transformer step downs the voltage to a safe limit value here now. It is going to step down the value into safe value, safe limit value from 400 kV to 110 volts, 100 volts, like that. For the safe value we can operate. Can you tell me, any one of you in your houses, how much voltage is there? Everyone, you are using the electricity. What is your house voltage, residential voltage level? आपके घर में अभी मोबाइल चार्जिंग यूज करते हो, पॉइंट में कितना वोल्टेज आते हैं? Can anyone tell? Then what you are studying in the power system then?
240.
Very good. 240 or 230 volts, 220 to 240. In between, we are going to use that is a single phase voltage. So less than that also we are getting here by using a potential transformer for the measurement purpose only. We can measure the power, energy, voltage, current. Based on that, we are going to step down the voltage level. Less than that means around 100 volts here now, 0 to 110 volts we are getting here now. So this voltmeter, it has very large resistance we are going to use here now. And the transformer step down the voltage to a safe limit value. 100 volt is safer only. We are using for our residential purposes 240 volts we are using, but for the measurement we are reducing into 110 volt. That is safer limit only. It is not harmful over there. So for the safe limit value, we are going to step down that one, which can be easily measured by the ordinary low voltage instrument like voltmeter, wattmeter, watt hour meter. We can measure that one. Next one. The potential transformer is made with high quality core here now. Why the high quality core is required? The flux density should be low over there here now, because the operating core at low flux density we are going to operate here now. For that reason, for the low flux density, the required core should be high quality. If the high quality core is there, then the flux density will be low, so that magnetizing current will be small. We want to get the current also, small current we have to receive over there. High voltage current is not necessary here. The low voltage current is required. For that reason, by using the high quality of core material, the low flux density is there. So based on that, the magnetizing current is very small over there. So the potential transformer is made with high quality core operating at low flux density. It is going to operate at low flux density also, so that the magnetizing current is small here. Now the terminal of the transformer should be designed so that the variation of the voltage ratio with load is minimum, and phase shift between input and output is also minimum here now. See the terminals, whatever the secondary terminals we are using here now, those are designed that so that the variation of the voltage ratio, we can vary the voltage also by increasing the number of turns, decreasing, like that also. So the ratio with load is minimum here now. The voltage ratio with load as comparing to the load also it is minimum. So if the voltage ratio is low, then the phase shift between input and output will be voltage also it is minimum here. The next point, the primary of potential transformer is having large number of turns. I already told it has, as by seeing the diagram itself, we can understand that here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 turns are there here. So here 1, 2, 3. Only 3 turns are there in the secondary. The 11 turns are there for the primary. So the primary is having large number of turns here now. Just for understanding, I have considered L1 and 3 here now. But in the practically, we are going to use thousands and 1200, 2000 turns we can use in the primary side over there. So the primary is connected across the line voltage, that is called the power supply line. It is connected here now. So generally between line and earth, we are going to connect the primary winding here now. So potential transformer primary winding is having large number of turns and it is connected across the power line. So and other terminal it is connected to the earth. So the generally the voltage between this point, the power line and earth, we are going to measure that. We are not measure, we are going to tap that one over there. So hence sometimes it is also called as parallel transformer here. It is connected in series or parallel here now. The primary winding is connected in series or parallel. Yes. It is connected in series or parallel. Series means one end here and another one. I will draw one example here. Here, suppose this is the line is there. Okay. If I want to connect in series means the wires I have to cut here now and I have to add the primary winding here. That is called series here now. That is called series. If the up to this one it is connected, it is going to the load side, then also I will tap this one here now. I will tap and I will connect one winding here. So across the earth I am providing means it is a parallel branch only. It is parallel branch only. So the primary is connected in parallel with the line here now. So for that reason, sometimes this transformer we are going to call as the parallel transformer. We are going to call that one here. Sometimes it is called as parallel transformer. See here, hence sometimes it is also called the parallel transformer here. Next one. The secondary of the potential transformer is having very few turns here now and connected directly to a voltmeter. The secondary winding of the potential transformer, it is connected to the only few number of turns it is connected and it is directly connected to the voltmeter. So as the voltmeter is having the very large resistance it has. I told in the while doing the diagram, I'll explain the diagram itself. The voltmeter, whatever which is connected, it is having a large resistance here now. Hence, the secondary of the potential transformer almost in open circuited condition here now. It is going to operate in open circuited condition only here now. How it is open circuit condition here? See here the voltmeter is there. It has very large resistance. Very large resistance means it will act as open circuit. Yes. The resistance is very large. Resistance is very large means which is opposing to the flow of current here now. So minimum current will flow here. The minimum current is flowing means that is open circuit or short circuit. I'm asking to you people only.
Open circuit.
Open circuit. So for that reason only what we are telling here now, hence the secondary of potential transformer operates almost in open circuited condition here. It is going to operate in open circuited condition here now. One terminal of the secondary of potential transformer is earth to maintain the secondary voltage with respect to earth here. With respect to the earth or with respect to the ground or with respect to the neutral, we are going to call that one here now. So we are going to maintain the voltage that is 0 to 110 volts here now. So other terminal is earth over there here now. So the insulation cost is also reduced by dividing the primary winding into sections, which reduced the insulation between the layers here now. The primary windings we are going to do in sections here now. For that one, by doing that one, the insulation of that rate we can reduce here now. Based on that, now what we have to draw? We have to draw the equivalent diagram of the potential transformer here. Same equivalent diagram, whatever we have used for the current transformer, here also we are using same one only. But here we are going to consider the voltage here now. Secondary voltage, EMF induced here, EMF induced in the primary, and applied voltage, that is called VP here. So the VP is the primary side applied voltage, supply voltage. The current flowing through the primary winding called, that is called IP here now. The RP is the resistance of primary winding, XP is the resistance of, reactance of the primary winding here now. Here some I naught is there. I naught means there is no load at the secondary here. On no load condition, the I naught current we are going to use. The I naught current is the sum of the magnetizing current and external lead resistance. It is going to current flowing through the leads and all the things. That is external current we are going to call it. So I naught is no load current. No load current is the summation of magnetizing current and external current here. So I naught equal to Im plus IE we can write here now. So the primary current is the combination of no load current and the N into IS, that is called we are considering the current means N is divided by IS for the current reverses IS into N we are going to use. Divide for the voltage system here now. For the potential transformer, we are going to use for the current reverses IS by N. For the voltage reverses, we are going to use N into Vs here. N is nothing but what? The ratio we are using, na? That ratio or number of ratio only. IP divided by IS equal to N we are going to use. Based on that, this N, the ratio, we are going to divide for the currents and we are going to multiply for the voltages for the secondary. So IP is combination of I naught plus IS here now. Because of this IP only, the magnetizing current or no load current will flow here now. And because of whenever this current will flow, the flux will produces. Because of that, the induced EMF will be inducers. So because of this IP only, the IS will flow here now. IS divided by N we are going to consider. That is called the IP is the combination of IS by N plus I naught. I naught is the combination of IE plus IM here now. First, we have to draw this currents phasor diagram. We'll draw here now. We will draw here now. It is a magnetizing means inductive coils only we are using here now. So we am considering the flux as the reference line I have taking. I am taking the flux line here now. And the IM is in flux, magnetizing current in the magnetic field is both are in phase here now. So I will draw the IM here now. The magnetizing current which is in phase with the flux, which is in phase with the flux here now. Next, the IE, here the resistive load is there or inductive load is there? The resistance is there here now. So comparing this IM, the IE is leads IM by 90 degree here now. IE leads IM by 90 degree here now. So the 90 degree I will consider, that is IE leads here now. So this point and this point, the total sum we are going to consider as I naught here now. So I naught not exactly 90 degree here now, because of this is a magnetizing coil only, inductive coil only, but it is not 90 degree. It is less than 90 degree, the I naught into there. So this I naught we have derived here. Before that, I have forgotten to take that these conditions, actually parameters. What I mean by flux means working flux, it is nothing. Phi is nothing but working plus. IM is the magnetizing component of no load. It is also called as exciting current we are going to call. I is the iron loss component of no load here. Whatever the iron loss, that is also exciting current only. I naught is the no load current here now. So for the excitation system, three currents are there. One is magnetizing current, another one is iron loss component current, and third one is no load current here. So the no load current is the combination of, it is a summation of magnetizing and iron loss component current here. So this is the excitation system here. Next, ES is the EMF induced in the secondary winding. VS is the secondary winding terminal voltage here. Now, at the output side, whatever the voltage is there here. NP is the primary winding turns. NS is the secondary winding turns here. Now, IS is the secondary winding current flowing through the secondary winding. RS is the secondary of the resistance, secondary winding resistance. XS is the reactance of secondary winding. RE is the resistance of secondary load circuit, and XE is resistance of secondary load circuit here now. and the phase is the delta is the phase angle of secondary load circuit, that is called tan inverse of XS by RS here now. That is secondary winding phase angle here now. Secondary phase angle. EP is the primary winding induced EMF, IP is the primary winding current, RP is the resistance of primary winding, XP is the reactance of the primary winding here now. These all are there here only. Resistance of primary winding, in reactance of primary winding. This is the iron loss component current. This is magnetizing current. This is no load current here now. The supply voltage. This is EMF induced in the primary winding. Magnetizing flux here now. And this one is the secondary current flowing through the secondary winding. Secondary winding resistance. Secondary winding reactance. This is the resistance across load and reactance of the load here now. And VS is the terminal voltage at the secondary load side, and this is EMF induced in the secondary. All terminals are clear here now. What do you mean by this VP IP means? Is it clear? If you understood this, then one only can draw the phasor diagram. Mute किया क्या मैंने? Unmute किया ना? Is it audible?
Yes, sir.
Okay.
Yes, sir.
See, all the terminals are clear. See, by seeing the circuit diagram itself, we can draw the phasor diagram. First, we have to draw this IP consider karne ka. IP consider this IP, it is a combination of I naught and this one here now. So for that reason, middle point, the flux magnetizing base, this whole operation is depends on this magnetizing flux only. So I will consider the flux as reference here now. I will consider the flux as reference. I will consider here now. So based on that, next we have to draw this I naught here now. I naught is combination of IE and IM here now. So IE is the resistance is there. So IM is magnetizing here now. So magnetizing and flux both are in phase here now. I will consider somewhere here now. That is IM here now. And I will consider the IE is leads the IM 90 degree here now. So I will 90 degree, I will take that one. The summation of this one and this one, the algebraic sum of these two, it will create the I naught value. It is going to create the I naught value here. Actually, this quadrant 1 is operating for the primary and quadrant 3 is operating for the secondary here. So secondary current I will consider as IS here now, and see here now the primary current voltage and the current here now. This current here now, whatever the magnetizing current is there here, both are 90 degree difference we are going to use here now. So the voltage induced EMF in the primary, that is called, it is 90 degree leads the magnetizing current here, because magnetizing means it is inductance is there here now, and the voltage for the inductive load, voltage leads the current or lags the current? Voltage. See, if you know the voltage, resistance, inductance, capacitance, what is leading, what is lagging, then only you will understand the phasor diagram. Otherwise, it is very difficult to understand here. For the inductive load, current lags the voltage or voltage leads the current. ये याद रखो, दोनों सेम है. Current lags the voltage means current voltage का पीछे है, और voltage leads the current means voltage current से आगे है. दोनों सेम है ना? The pronunciation, whatever how you are tell, that is depends here now. Based on this, I can say that the voltage leads the current here now. Like that, we are going to call voltage is leading, current is lagging here. Voltage is leading, current is lagging for the inductive load only here now. So EP we are going to consider. Same for the secondary here now. Here also the inductive load is there. So we are going to consider for the third quadrant, primary and secondary in the opposition direction here now. So this is VS or ES we are going to consider here now. And the IS, it is going to lags by some angle, we are going to call that one here. Some angle, but it is not exactly 90 degree here now. But ISRS is and ISXS, comparing these two, it is going to 90 degree, we are going to draw. Here, yes, we have to consider. Yes.
So potential transformation की slide दिख रही है.
Which one?
Potential transmitter.
Potential
Transformer.
transformer.
हाँ.
हाँ.
वही slide दिख रही है क्या? Slide change की थी क्या आपने?
Change नहीं दिख रहा है क्या? Phasor diagram नहीं दिख रहे?
नहीं सर वही स्लाइड दिख रही है।
ऐसा है क्या? ये फेजर डायग्राम नहीं दिख रहा था क्या आपको?
नहीं दिख रहा था सर, आप भी दिखा।
अरे पहले ही बोलना था ना, फिर उसके लिए।
नहीं सर हमको लगा वही पर एक्सप्लेन करेगा।
वही कहाँ है? एक्सपी आरपी कहाँ है उधर पोटेंशियल ट्रांसफार्मर में? एक मिनट, आई विल स्टॉप शेयरिंग एंड वंस अगेन आई विल शेयर। अभी कौन सा स्लाइड दिख रहे बोलो? क्या दिख रहे? कोई तो रीड करो प्लीज, एनीवन ऑफ यू रीड। Which slide is visible?
Phi is equals to working flux.
हाँ, अभी चेक करो, अभी कौन सा क्या स्लाइड, कौन सा स्लाइड विजिबल है?
Sir, equivalent circuit of a potential
ठीक है
transformer.
This diagram is visible?
Yes, sir.
Oh, this one only I was explaining up to here now. This is the resistance of the primary winding. This is the reactance of the primary winding. The current flowing through the primary winding. Voltage supply voltage given to the primary winding. This is the iron loss component current here. Now this is the magnetizing current, and this is no load current here now. This belongs to the primary here now, and EMF induced in the primary is EP here now. This EMF induced in the secondary is ES. Current flowing through the secondary winding is IS. The resistance of the secondary winding, reactance of the secondary winding, external load of resistance RE, and external, that is reactance, load reactance, that is called XC here now. And the voltage across the load, that is called VS, we are going to consider. These all terminals are there here now. First, on the primary side, we are going to draw in this first quadrant, and the secondary we are going to draw in the third quadrant here now. So the both are in reversing order, it is there here now. So the current flowing through the IP is up to here, it will flow here now. Some current will flow here and some current will flow here. So first we will draw this current here now. I naught, the no load current, is the combination of iron component plus magnetizing current here. Now for the iron component, the resistance is there. For the magnetizing current, inductance is there here now. The coil is there, inductive coil here now. And this is also the inductive coil is there. So middle combination of both for the primary and secondary, it is linked here is phi is there. That is called magnetic flux. The x-axis I will take as magnetizing flux, I will consider here now. So IM is in phase with magnetizing flux. IM is in phase with magnetizing flux. I will draw here IM. Next, if IM I am taking the reference, means here inductive coil is there, here resistance is there. So the current flowing through this resistance leads the IM here now, leads the IM by 90 degree. So I have to draw this one as upper side here now, this 90 degree here now. And combination of IE plus IM, it is going to give the I naught value, it is going to give here. I naught value, it is going to give here. Next, what we have to do, the induced EMF, and it is an inductive load. The current I naught or IM magnetizing current only we are considering starting here now, because of the magnetizing current only the EMF will be induced here now. So as compared to the magnetizing current here now, the voltage or induced EMF in the coil that leads the current IM by 90 degree here now. So the IEP, we are going to extend this part here now. So it is leads the current IM by 90 degree. That is called EM. EP we have considered here. EP. Okay. So next, I naught and EP we have derived here now. So I naught is over. Next, IP is the combination of I naught plus this flux and into IS here now. Flux is nothing but the ratio we are going to consider for the current. Reverse current is here. Actually here the IS is there. Whenever here I will take the reverse component of this one here now, we should have to divide N by IS. For the current we should have to divide N. For the voltages we should have to multiply the N here. Now if VS I want to take here, means this line, just a minute I will tell. This VS is there, I want to take in the opposite reverse side here now, it will become NVS. So I have taken this IS current, I have taken into the reverse order here now, it will become IS by N here, IS by N here now. So the IP is the combination of I naught and this IS by N here now, IS by N here now. So IS by N we have taken here, and I naught is already taken here now. The summation of these 2 points, average of these 2 points, it is going to give the primary current, that is called IP. It is going to give here. It will give the IP value here now. The IP value here it is going to give here. Next, the induced EMF we have drawn here now. Induced EMF is we have drawn here now. Voltage drop across this coil here now. EMF induced here now. So the voltage drop across this RP is IPRP. We can draw here. The IPRP voltage drop across this one here now. So it is little the angle it is there with the I naught only here. It will be there with the I naught here now. So I will draw here IPRP here now. IPRP here now. So what is this one? This is a resistive load. Is this resistive load? This is resistive only, na?
Yes, sir.
This one is inductive here now. So voltage drop across this one is resistive here now, IPRP, and but this IPRP it should have to leads 90 degree here now. This voltage should have to lead 90 degree because it is inductive load, it is a resistive load here now. So IPRP I have written here now, from 90 degree, above 90 degree, we are going to give, that is called IPXP here. Here in between these two 90 degrees there.
Yes, sir.
In between these two 90 degrees there, that is called IPXP here now. So the EMF induced and voltage drop across RP, voltage drop across XP, this will give the total voltage, that is called VP. VP equal to IPRP plus XP, IP plus EP here now. So this complete summation it is going to give, that is called VP here now. So we will join this one as from O to point. This one will give the VP here now. That is called primary voltage here. So this primary side it is over now here. Same thing we have to draw here now. So the ES we are going to take the 90 degree of the magnetizing current in the reverse order here now. From the flux it is 90 degree here now. Leads we are going to call here, anti-clockwise we are going to consider, means it is leading and this one is lagging here. So next the VS we are going to consider, that is voltage drop across this load here. This voltage drop means because of this ES only the voltage is considering here. Voltage is considering here. So VS plus ISXS plus ISRS, it is total voltage, that is called ES we are going to get here. So what I will draw first, I will draw VS. Next, for some angle with IS, I will draw ISRS, and this one is resistive load and inductive load here now. Then this IXXS, it is going to again 90 degree difference is there. The summation of VS plus ISRS plus ISXS, it is going to give the ES value here now. EMF induced in the secondary, that is called EFC. So this is the phasor diagram representation of the potential transformer. But this phasor diagram, it is not yet completed. We have to derive the equations. This whatever this ES, VS is there, I have to take in the reverse order. We have to take this one. This equation also I have to draw equation. I have to draw in this side. In the primary side only I have to take that one. For that reason, what we have done, the reforming the phasor diagram of that enlarged the and consigned phasor diagram of the potential diagram. So this one here, IS and IP and I naught, IM, this part I have kept as it is here now. This is IP, I have kept as it is here now. But whatever the VS term is there, I have taken in the reverse order, that is become VS N ho gaye. Next ISRS into N ho gaye, ISXS into N ho gaye. Other things are same only. Just I have taken here ES and VSN and this ISXS here. Now whatever this part is there, this part I have taken into primary side also. This part extra it is came here. So based on this, I have made the terminals number here. Now this one I have considered as A, this one I have considered as B, this one I have considered as C, and this one I have considered as D, this one I have considered as E, and this is O here. So from this, we are going to derive the transformation ratio equation here. From this phasor diagram, we are going to derive the transformation ratio equation. We are going to derive here. So we'll start the derivation. Secondary voltage when prepared to the primary side are to be multiplied by N here. Secondary voltage whenever it is going to prepared by primary, so voltages will be multiplied by N. But when secondary currents are referred to primary side, This is 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 there. Is by n we have to use here. No, it is missed here. देखो, is by n नहीं है, only is है, but it is actually is by n we have to write here. Okay, it is mismatched here. So the primary side, they must be divided by n here. So actual transformation ratio we are going to consider here now. Theta, where is the theta? This is the theta here now. It is angle, phase angle of the transformer here now. Total phase angle of the transformer, that is called theta, that is between VP and VS here now. This is VP and this is VS here now. This VP
Sir.
is there. Yes.
जावा स्टूडेंट वेटिंग रूम में है
उनका जावा नहीं है क्या?
सर, उन लोगों ने जावा लिया है ना, तो उनके लेक्चर्स होते हैं अभी।
नहीं, लेक्चर्स हो जाएगा। कोई नहीं ना वेटिंग रूम में भी। I have unlocked the meeting now. I will remove the waiting room में remove कर देता हूँ, ठीक है? Okay. So based on that, we are going to the theta is the phase angle of transformer, that is called angle between the primary voltage and secondary voltage, and delta is the angle of secondary load circuit. This is the delta secondary load circuit here now, and beta is the phase angle between IP and VS here now. This is the IP and this is the VS here now, this one. So beta is the angle between IP and VS here now. Now OA, where is the O? This is O. Here A is there. That is called, see here, you consider only this triangle, you consider here now. This triangle, this one, whatever I will draw the red line, you consider this triangle. So here it is a VP is there. Here VP is VP, and here the angle is there, theta here. Angle is theta here. Okay, this one is, we can write VP sine theta. This one B to A, that is called VP sine theta लिख सकते हैं. And this one is VP cos theta. Yes or no? VP cos theta here. See here the angle, the opposite, the reactive component, this is the real component we have studied in the first year. Real component will be VP, this hypotenuse value into cos theta. Reactive component is hypotenuse value into sin theta here. That is called here. Yes, we can write like this. Only this triangle I am telling here now. Whatever red line is there, you consider that. Here the angle is there. So this one already we have derived, this is called VP is there here now. So the reactive opposite side, it is called reactive component. The adjacent is the real component. The real component is VP cos theta, and a reactance component is VP sin theta here. No, so O to A, which one is OA? This is O here. No, this one is A here. No, so OA equal to VP cos theta, we can write like this. Yes.
Yes, sir.
OA equal to VP cos theta here. On this one is over now. I will close here, erase that one all. So this OA is there. OA, O to A, we have to measure here now. So how we can measure this one here now? O to A means first we have to write this one here now. N into Vs up to here. Where it went? Up to here we have to write NVS. Then we have to go like this. Then this is IS NS into cos delta here now. Where is the delta? This one is delta. So here the delta will come here now. So this is the real component of this delta, and this one is a reactive component of delta here now. Then we have to go like this. Then we have to go like this. Then we have to go like this. So equivalent of OA is up to here. According to VP, we are considering the OA here now, VP cos theta. So this value we are going to do like this here. So we have to consider this one. The angle beta is used here now. So IPRP cos beta, IPXP sin beta we have to use. So this equation OA equal to NVS up to here. It is NVS is there. I will write NVS. NEVS is over. Next IS RS N into cos delta here now. This is the real component. N into IS RS cos delta. Next this con n into is xs sine delta here, no, sine delta. Next it will go here, no, IPRP, the opposite here, no, adjacent here, no, this one, this is opposite, equivalent to this one we are going to consider here, no, this is equal to this one here, no, IPRP cos delta, IPRP cos delta. Next IPRP sine delta here, no, IPRP sine delta. It completes the OA value here. It completes the OA value here, no, n vs ns rs cos delta, ns xs cos sine delta, IPRP cos delta, cos beta, and IPXP sine beta here. Now next we have already derived this OA equal to VP cos theta here. No, I will write this is VP cos theta into n vs is, same value I have substituted here. No, from this one, see here, NIS you can take common, here also NIS you can take common. So the term left is RS cos delta plus XS sine delta, you keep as it is, and IPRP cos beta and IPXP sine beta you keep as it is. The next slide, what we are going to do, very point. See here, from the angle OCD, OCD means this one here, no, OCD here, no, that is called beta we are going to consider here, no, and that is OED, that is called delta we are going to consider here. OCD is beta and ECD is delta here, no. So OCD is nothing but, where it is, OCD here, no, OCD we are going to consider here, no. Based on that, here IP is there, the CP we can tell that one here, the delta is here, means CP equal to IP cos beta, IP cos beta we can write this one, IP cos beta, this is IP sine beta here, no. So OCD equal to, or nothing but CD equal to IP cos beta plus which current, it is nothing but, for the horizontal we are going to consider first IE we are going to consider, this one is, this value is IE plus IE IS by N here, no, this is this one equal to this one here, IS by N cos delta here. So IP cos beta equal to IE plus IS by N. Similarly, IP sine beta equal to IM plus IS by N sine delta here. These two equations we have derived. Why we have derived these two equations means, see here, you remember this one, IP cos beta and IP sine beta. In the previous equation, whatever we have used, previous equation may we have, is there the term here, no, IP cos beta is there here, and either IP cos beta, this line, I will take the marker pen. Here IP cos beta is there, here IP sine beta is there. In this place of IP cos beta we have to substitute that value, and IP sine beta we have to substitute that value, we have to substitute here now. This IP sine beta you have to substitute this one, IP cos beta you have to substitute this one here, no, and VP cos theta equal to VP only here. If cos theta equal to 1, the phase power factor is 1, then VP cos beta equal to VP only we are going to consider, because cos theta equal to 1 here, no. Now the LHS side VP cos theta, it is nothing but VP, and NVS as it is, NIA RS here now. See here, we have substituted directly, they have substituted the value here, no. RA cos delta they have considered common here, no. XS sine delta by taking NS as it is here, no. In the place of IP cos beta, I have substituted IE plus IS by N cos delta into RP plus, in the place of IP sine delta, I have substituted this IM plus IS by N cos delta. It is not cos here, no. Again, print mistakes are there. So many print mistakes are there in the textbook. Don't, while using, if you are confident, then only you have to use here. This is called sine again. This is called sine here now. Sine delta it is. Okay, into XP here now. See here, NVS I will write as it is here now. NVS I will write as it is here now. And from this one, NIS RS cos delta, NIS IRS cos delta. So IS N and cos delta I will take common here now. IS cos delta I will take common, means which is the term left? N into RS is left here now. N into RS, I will write N into RS here now. From this one, RP is by n cos delta is there. So if is cos delta I will take outside is nothing but RP by n is the left term. I'll write here now RP by n here now. This term is over. Similarly here is sin delta you take common, is sin delta. So xs into n, it is left here now, xs n we have written here now. From this one is sin delta you take common here now, is sin delta, xp by n is there, xp by n we have written. So IE, RP, IM, XP here now. This is the complete term, it is going to left here now. Next what you do, n vs you write as it is. This is by taking the LCM of this one here now, it is total divided by n, it will become n square here now. Here also total divided by n, it will become n square here now. LCM liya to. So that is is by n I will write here, is by n cos delta as it is, n square rs plus rp. Here is by n sin delta, n square xs plus xp here now, plus IERP plus IMXP. So this will give the final equation of the, so this n square rs plus rp here now. Is there any inductance reactance term here? Isme reactance term hai kya? No, here also rs is there, here also rp is there. So I will consider as this is total resistance of the primary, that is rp, and here only reactance term is there, xs and xp here now. I will consider this one as that is primary reactance here now. So the total primary voltage, that is called Vp, equal to n vs plus is by n cos delta into rp plus what is this one, is by n sin delta into xp plus IERP and IMXP here. This is the final equation of Vp here now. So based on this one, what we have to do, we have to calculate the equation that is called transformation ratio, we have to calculate here now. So we know the transformation ratio, that is called Vp by Vs here now. So in the place of Vp, you substitute this whole equation, Vp you substitute divided by Vs here now. By doing that one here, n Vs by Vs is nothing but only n term will left here now, that is n plus is by in, this is by Vp, and Vs only this one we have considered here now. So by doing this one, I will take R here, already actual ratio is, transformation ratio is R here now. When I will send this n into this side here now, R minus n it will become here now. So is by n and rp, this one same equation we can write here now. So this one n into is r cos delta plus xs, and this all the things we can write the equations here now. Can write equations here now by reversing the equations. This is the final equation for the transformation ratio here now, for the transformation ratio here now. So similarly, by considering the theta here now, again we have to consider the OA, that is called tan theta equal to AB by OA here now. What is the time? Okay, time to ho gaye. OB by AB by OA. AB value we have to substitute from the phasor diagram. OA value we have to substitute from the phasor diagram. And for the, since theta equal to tan theta, on that condition, again we are going to get the phase angle equation here, is by Vs xs cos delta minus rs sin delta plus IEXP minus IMRP. By deriving this equation, complete equation, we are going to get the phase angle here. So the equation for the error is same like a CT only. The whatever the ratio error is there, it is the combination of the difference between the actual ratio and nominal ratio here. No, Kn is nothing but nominal ratio minus actual ratio divided by actual ratio. That is called percentage of ratio error into 100. We are going to call ratio error. We are going to call whatever the phase angle is there, phase angle equation, it is give the phase angle error equation, it is going to give here. So it completes the potential transformer whole. It is completed here now. And in the tomorrow class, we will take one problem on this, and only in the current transformer we will take one problem, that is important problem is there, and we'll discuss about difference between current transformer and potential transformer will discuss, and I will stop here only. See, एक class miss करके explain करने के लिए गए ना, it will not understand to you peoples actually. It should be continuous. Who were present for the starting, only 14 members was present. Now the strength is 22. I don't know how many of you were joined. Rule number 1, you were not present previously. 1, 2, 4. Nine is absent. 11, 12, 13, 14, 15, 17, 19 is present. 20, 21, 22, 23, 24, 24, 25, 26, 27, 28, 29 is present. 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 43, 44. So many students are absent. Okay, I will stop here only and we'll continue next class.